In this review of Chapter 6, I want to focus on the most important types of calculations that you're going to see here, you see on the test. These calculations, many of them anyway, will be used in future chapters as well. And the calculations really center around this concept of a mole. So what I want to do is I want to work through this problem, of course, but I also want to sort of expand and use this problem and use gold and the information in the periodic table to sort of put all of the pieces together in a single package, okay? And then we'll do the calculation. So a mole is just a certain amount, and we call that Avogadro's number. And sometimes you'll see this abbreviation for Avogadro's number, and it is a very large number. Now, the units on this can be anything. Can be atoms, can be ions, can be electrons, can be cupcakes. It doesn't matter. So here, since we're dealing with gold, which is an atom, we'll put atoms there. Now, that particular amount there just happens to equal 1 mole of a sample. And it would be analogous to, 12 atoms would equal 1 dozen of atoms. Dozen and moles are analogous to each other. It's just a large number that we use to start counting up these different substances. And again, it can be used for atoms, ions, molecules, whatever is given in the problem. Now actually, we have enough information here to actually do the calculation. But I want to do something else. I'll do the calculation, sure, but I want to expand on this topic just a little bit. Like, for example, I can count atoms. So let me just move that down here. So this is, like number of atoms. Like I could physically count 1, 2, 3, right? It's just an amount. And what else do we know about gold? Let's look at the periodic table. There's gold. It's hard to see, but it's about 196 AMU. Or let me use a mass that we're more familiar with in the laboratory, and that's grams, right? As it turns out, this number here, all of the numbers, okay, are telling us information actually about the number of moles for a given element. And what do I mean by that? Well, that 196.97, which I always like to carry out to the hundredths position, grams, that just happens to equal 1 mole of the sample. What did I say up here? Well, 1 mole of the sample just happens to equal this number of atoms. Okay, so then I can say this is true as well. So if I go into the laboratory and I have a sample of gold, be nice, I don't, and if I weighed out 196.97 grams on the balance, then I can be pretty sure that I'm at least this close to that number. Okay, this is only 3 significant figures of a very large number. In the grand scheme of things, it's not super accurate, but it's good enough for us. Okay, it works for all of our calculations. But that's all it is. It is a counting device that allows us to relate something that we talk about, something we talk about in the laboratory to something physically that we can count. All right. So this mole here, sometimes you'll hear me say it's the middleman. And it is. It's the one that you often calculate in the first step. When in doubt, calculate number of moles. Because once you have the number of moles, it allows you to transition to a lot of different values in your calculation. Now for Chapter 6, we're just going to be primarily playing with this kind of game, jumping back and forth between the number of atoms or molecules or ions. Again, right? Avogadro's number can be applied to anything, just like 1 dozen can be applied to anything. Bagels, donuts, atoms. You could count 12 of anything, right? Enough said. Let's do the calculation. Now I want to go from moles to the number of atoms. So I want to go from moles to the number of atoms, or moles to the number of atoms. Why am I doing this? This is a conversion factor. This is going to look a lot like the dimensional analysis calculations. This is a dimensional analysis calculation that we first learned in Chapter 2. So what do we do in Chapter 2? Well, we start with the data that's given. So this would be 8.83 times 10 to the minus 2. This is moles. And what did we do for dimensional analysis? Well, we grabbed our conversion factor like we have here. The unit that we're starting with, mole, that portion of the conversion factor is going to go on the bottom. And then the other portion of the conversion factor is going to go on top. Why was this so useful? Well, because it allowed me to keep track of my math. I refer to this as a mathematical template. All it's doing is if I have it set up right, which I do, right, moles divided by moles, moles cancel out. I'm left with atoms, which is what this problem is asking for. And now I just have to do the calculation. I'm going to multiply these two numbers together to get my final answer. Quick word about significant figures. 3 sig figs in the data, 3 sig figs in our final answer. Conversion factors, ignore sig figs. And that'll work out pretty well for us. In this video, let's do one more, a calculation that's dealing with Avogadro's number. And this is one where we're going to go now the full scale here. Now I'm not going to rewrite this every single time I do a calculation. Just know, atoms to moles to grams. That is the pattern. And in every example, if you're not given the number of moles, then the first step is probably calculate the number of moles. And you certainly see it in this next example. So we want to go from, well, we want to go from atoms to mass. And the mass here is going to be in grams. What information do we have? Okay, so again, for the test, you'd have a periodic table. You have Avogadro's number. Right? And I said anytime atoms, molecules, if you're counting atoms or molecules, Avogadro's number is going to be involved. And for us, since we're dealing with helium atoms, we're dealing with atoms, this amount is always equal to 1 mole. The other bit of information we have is actually from the periodic table. It's that guy, 4.00. So we know that helium has a molar mass of 4.00 grams per mole. So when you see this unit here, this is what we're talking about, molar mass. How much does one mole weigh? Right, that molar mass, I mean, what it's trying to get at is that, right, if I go in and I weigh out 4 grams of helium exactly, then I'm going to have 1 mole of the sample. How much does 1 mole weigh? Well, 1 mole weighs 4 grams. Why is this relevant? Well, because we have our middleman here. Right, we have 2 conversion factors here that's going to allow us to go from atoms to moles to grams, finally, just like we saw in Chapter 2. Much different units, numbers are different, but the math and the conceptual thinking is the same. The logic is the same here. So just like in Chapter 2, we start with what's given, start with our data. These are atoms. I got 2 steps. I'm going to have 2 setups on my dimensional analysis. First one, atoms to moles, it's up here. I start with atoms this time, so then atoms is going to be on the bottom. So I'm going to divide by Avogadro's number here. And that's equal to 1 mole. Right, if I just pause for a second, right, atoms going to cancel out. Now I have moles. What's the relationship? Well, 1 mole equals 4 grams. This is going to go on the bottom, and its partner, the other half of the conversion factor, is going to go on top. If I look at how my units cancel out, moles divided by moles, we get rid of that. And now what do I have? I have grams, which is what I want. And then if I do the calculation, right, what this is telling me is that I'm going to divide by Avogadro's number and I'm going to multiply by 4 on my calculator. I ignore sig figs for my conversion factors, so that means my final answer, I'm going to round to 3 significant figures. And this comes in at 8.17 grams. 8 is greater than 4. Well, because 10 to the plus 24 is greater than 10 to the plus 23. So, you know, you can anticipate this is more than 1 mole, so it's going to weigh more than 4 grams in the case of helium. In the other videos, we'll do more with molecules and also empirical formula determination. Okay, thanks.